The second one is about my another research project, which is traffic risk management or traffic risk estimation using the AI. But this presentation will start from what is traffic risk and traffic information provision. And then in the later part of this presentation, I will explain the traffic risk estimation using some AI technologies. And let me start from some general introduction. So this diagram is a trend of the traffic accident in Japan. So x-axis is year until 2012. So this data is a little old, but the trend is same. And the red one is the number of accidents, and blue one is the number of injuries, and the green one is fatalities, which is right-hand numbers. Okay, but anyway, so this is a trend of traffic accident in Japan. And the number of accidents in Japan rapidly increased during this period from 1948 until 1970, when Japan experienced rapid economic growth, and also the car ownership increased rapidly in this time. And in this time, the road condition is not really good, but the car ownership just rapidly increased. And so many people have actually injured, or number of deaths was also increased. But during this period, we experienced a decreased trend of the number of accidents or number of injuries. And during this, from 1970 to 1982, they did the intensive investment on the safety facilities. So during this period, they installed many guardrails or pedestrian walks. Yeah, they did very intensive investment for the traffic safety. And these years, mainly, so this decrease in this period is mainly due to the safety education for safety. And also another reason is the introduction of the advanced safety vehicles, okay, like automatic brakes. So Japan experienced the rapid increase of the number of accidents, but these days the number of accidents is decreasing trend. And in 2023, the number have decreased up to this level. But still, so the number of accidents is actually decreasing, but still there are many accidents in Japan. And the problem is the number of accidents decreased, but there are many locations with small number of accidents. So that's difficulties in these days. So I will show that using this conceptual diagram. And x-axis is location ranked by accident frequency, okay? And y-axis is the number of accidents at each location. And in the number of accidents is quite high in some of the location. We see many accidents, but in many other locations, we only see small number of accidents. So that's a typical trend of the number of accidents by different location. And in the past, most of the safety measure was focusing on this part. So small number of location with many accidents. We only focus on these locations, okay? And we successfully decrease the number of accidents by doing the countermeasure for these locations. However, there still remains the many locations with small number of accidents. And we have to enhance road safety more, we have to decrease the number of accidents in this green region. Many locations with small number of accidents. Okay, so this is called long tail. So this red part is called short head. But to enhance more safety, we have to focus on this long tail. And how can we tackle with this long tail part of the accidents? So that's a question. And our current research approach for the traffic management is we want to somehow reduce this short tail, long tail. We have to focus on this long tail by using the accident risk information. So that's our recent research activity. And what is accident risk? Accident risk is the likelihood or probability of the accident occurrence at the location and the situation. And traditionally, it is called the accident rate. Accident rate is defined as by this equation. So number of accidents divided by the vehicle kilometer traveled. So basically, the accident risk is the same as the traditional accident rate. Okay, and the problem of the accident risk is, so this is not the number of accidents, but the probability of the accident. So this accident rate changes depending on the road structure, not only road structure, but also depending on the weather. In the rainy weather, we experience higher accident risk compared to the sunny weather, or traffic condition also affects the accident risk. So accident risk changes dynamically depending on the weather or the traffic conditions. Okay. So yeah, the accident risk is a kind of function of the traffic state or the weather or even the time of the day. It's a kind of the function of many factors. So yeah, this is the accident risk. And what is the accident risk information? To explain that, I will explain that using this slide. So in a road network, there are two players. The one player is the public sector. For example, the road administrator or traffic administrator. So that is one player of the road network. The other player is the driver. Okay, and it's like the seller and the buyer in a market economy. And this public sector try to maximize the social welfare. And so this is their objective function. And to maximize the social welfare, they provide the service to the drivers. Okay, so their service is a good network or good road condition. So that's the seller, what seller provides to the buyer. And what the buyer do, I mean the driver, what the driver do? Their objective is to maximize their personal gain. The driver try to go faster or go safer. So to maximize the personal gain is their objective. Okay, and so this is their objective, and they do their action. I mean, they drive to maximize their personal gain, and by their action, the road service condition changes. For example, if everyone want to use the road at the same time, then congestion happens. And if everyone drive faster, then accident may occur. So by their behavior, the road quality or road service changes. And in response to the quality and the road service, then the public sector do another countermeasure to maximize the social welfare and provide the good network. So this is what the public sector and the driver do in a network, in a road network. And the problem is, on the public sector side, they have very rich information about the traffic situation. Like they know where the accident happens or where the network is dangerous, or they know the travel time, kind of very good information about the network. Okay, but on the other hand, the driver, they do not actually know the network state. They do their behavior, they decide their behavior based on the limited information about the network. So this is a kind of information asymmetry situation. Okay, so because of this information asymmetry, so the road network normally experience a kind of market failure, and to resolve this market failure, the signaling is important. In this case, what is signaling? The signaling is information about the road network. Okay, so to make the road network better, this network information asymmetry should be resolved, and can be resolved by providing the information. So this is the importance of the information. Okay, And what is the risk information? So that's the topic of this presentation. And in normal road, in reality, we see this kind of information. So traffic information is like typically the travel time information. Like to the airport, by the motorway, it takes 20 minutes. By the normal arterial, it takes 30 minutes. So this kind of travel time information is what we see normally. Okay. And the accident risk information is similar to the travel time information. So we actually don't have this kind of information provided in the real world, but this is what we want to provide to the drivers. For example, probability of causing an accident on the motorway is this number, 0.002%. But on the other hand, if you take the signalized arterial, the probability of causing the accident can be a little higher, like 0.01. So this is accident risk information. And if we have such an information, if we have travel time information, based on this information, we choose the faster route. If you want to travel faster, then you take motorway. If you can go slower, you can take arterial. So based on this information, you can take the better action for you. You can maximize your gain. And also, if you have the accident risk information, you can make the better choice for your safety as well. Okay, and the network can be utilized better. So that's our expectation of providing the accident risk information. And let me show you the effect of the benefit of the accident risk information in a very, very simple and extreme case. And we have, let's say we are traveling from A to B, and we have two routes. One is the north route, which has higher accident risk. Another is the south route, which has a lower accident risk. And the accident risk of the north route is 10 accidents per 100 million vehicles. Okay. Accident risk is actually quite small, like this order, but 10 accidents, 100 million vehicles. So that is the north route. And the south route, we only have one accident per 100 million vehicles. And what happens if, okay, how many vehicles? Okay, the total traffic volume from A to B is 100 million vehicles per year. And if this 100 million demand is equally divided into north and south route, then what is the expected number of accidents? So we can simply calculate. So if 50 million take the north route and 50 million take the south route, then the total number of the accident per year becomes 5.5. Okay, so this is when this happens when they take both routes equally. But if all 100 million vehicles want to take the safer route, and if all of them take the south route, the number of accidents. Okay, if all the vehicles take the north route, the number of accidents becomes 10. But if all the vehicles use the south route, the number of accidents becomes only one vehicle. So, of course, this is quite extreme and too simple case. But general idea is like this. If people take the route with smaller accident risk, then it is natural to say that the number of accidents should decrease. Okay, so this is an idea for the traffic accident information provision. Okay, and to see how this accident risk information can change the number of accidents, we did some simulation works. So in this simulation, we have two route choice cases. So one is the normal route choice case. In the normal route choice case, the cost function of the driver is, of course, normal, like travel time or expressway fee and others. For example, the turning penalty. So, for example, they normally don't like the right turn, so the right turn has a higher penalty like this. So in a normal route choice case, the cost function is like this. And in the risk-based route choice case, in addition to this travel time, expressway fee, and others, they also consider the accident risk, cost of the accident risk, and they choose the best route considering accident risk in addition to the normal cost. So that is the accident risk-based route choice. Okay, and we did some simulation studies without accident risk information and with accident risk information. So I will show you one of the example later. Okay, so at least in a simulation, we can evaluate the effect of the accident risk information in a simulation environment. But accident risk information is not so simple. So, okay, this is one type of the accident risk information. So the probability of causing accident by motorway is 0.002%. But as you see, 0.002% is quite small. And if you take arterial, the accident risk is 0.01%. Okay, this number is slightly larger. Not slightly, but 5 times larger than motorway accident risk. But still, 0.01% is quite small. So even if you see this number, maybe 0.01% is, yes, it is larger than motorway, but still this number is quite small. So this number has nothing to do with you. You will never experience accidents. I think this is a very natural reaction to this small number of the probability. Okay, so accident risk information has actually very, very limited impact to the driver's route choice. Then what we can do, one way is to convert this accident risk probability into the monetary term. So we call this accident loss risk. If you take the motorway, you will lose your money. You will lose in a monetary term like this amount. If you take the arterial, your loss is this amount. So what would you do? So this is the accident loss information. And another type of the information we are thinking is the accident encounter risk. Okay, the original accident risk probability is the probability for you to cause the accident. For you to cause the accident, the probability is this amount, but the probability you see someone's accident is much higher actually. If there are many vehicles are driving in a road, each person has smaller probability of causing accident, but there are many people, you will see some accident of someone. And that accident encounter risk is, so due to that reason, the accident encounter risk is much higher than the accident risk. So if you try to compare 2% and 10%, then because the probability number is higher, so maybe, okay, if it is 10%, okay, you may take the motorway because it only has 2%. So accident encounter risk can be useful. So these are our proposal of the 3 types of accident risk information. Accident risk, so for you to cause the accident, or for you to encounter someone's accident, and monetary term. So these are 3 types of accident risk information we are proposing. But this accident risk and accident encounter risk is not actually equal. They are essentially different types of information. And we have to be very careful because these 2 types of information can cause a paradox. So I will explain what's the paradox. And the normal accident risk is called, or we can also say accident occurrence risk, where the risk, you cause the accident. So this is an accident risk. So in other words, this is your personal risk to causing the accident. So that is the accident occurrence risk. On the other hand, accident encounter risk is essentially different. So this is the risk of encountering someone's accident. So if there are more traffic volume exist on the road, then you will higher chance to encounter someone's risk. So this accident encounter risk is very similar to the number of accidents. Okay. If there are many vehicles driving, the number of accidents naturally increase. So accident encounter risk is something like that. And Again, let's think these two routes between A and B, north route and south route. North route has higher accident risk, and south route has lower accident risk. And the accident occurrence risk for you to cause the accident is like this much. North route is 2,000 and south route 1,000. But let's say if the traffic volume is like this, in the north route, traffic volume is 2.5 million and the number of accidents is 50. In this case, if we calculate the accident risk, it becomes 2,000, okay? And in the south route, traffic volume is much larger, 10 million, and the number of accidents is 100. In this case, if you calculate the accident risk, it's 1,000, okay? So this is the accident occurrence risk. But what is the accident encounter risk? In the north route, we have 50 accidents, okay? And on the other hand, in the south route, we have 100 accidents. So for you to encounter someone's accident is higher in the south route, okay? Your personal risk is smaller in the south route, but the chance you will encounter someone's risk is higher because the number of accidents in the south route is larger compared to the north route. Okay, so this is the essential difference of the accident occurrence risk and accident encounter risk. And this causes a paradoxical situation. And if you want to be safer, and if you want to take the route with smaller accident occurrence risk, then you will take the south route. If you want to drive safer, you will take the south route because the accident risk is smaller. But actually, the number of accidents is larger in the south route. Okay, so the choice you wishing to be safe can cause additional accident in the south route. Okay, so this is we call the paradoxical situation in this accident risk information. And yeah, this is caused because the accident risk is your personal risk, but accident encounter risk is a kind of social cost. And this difference causes such a paradoxical situation. So we have to be very careful in providing the accident risk. And okay, there can be the paradox when we provide the accident risk information. Then the question is, how much effect does the accident risk information actually have? And in which case we have such an undesirable paradoxical condition? So this is a question, and we investigated to answer these questions. So how much how much benefit we have by providing the accident risk information, and when we encounter the undesirable cases. And this is a study site and data, and we tested our idea for this network from Hiroshima to Kobe, and we have two expressway routes. One is called Chugoku Expressway North Route, and the other is the South Route Expressway. And the distance is longer in North Route, okay, and the South Route is shorter. And the North Route takes goes through the mountain. On the other hand, the South Route takes the coastal line mainly. So the geometry is better in the South Route. So the South Route has smaller accident risk. On the other hand, because North Route takes the mountain area, the accident risk is higher in the North Route. So that's the characteristics of these two routes, okay? And OD traffic volume between Hiroshima and Kobe is this much, about 4,000. And we did analysis for 2 different days. I mean, the one is a normal day, normal working day, and the other is a busy day. Busy day is during the holiday, during long holiday, when these routes experience heavy traffic congestion. Okay, and this is a travel time of North Route and South Route in normal day and busy day. In normal day, because North Route is longer compared to the South Route, and also North Route has the geometry of the North Route is bad. There are many curves and there are many uphill and downhill. So North Route takes longer travel time compared to the South Route in normal day. And on the other hand, in the busy day, even in the busy day, the travel time of the north route doesn't change that much. But in the south route, actually many people tend to use the south route. In the busy day, this route experiences quite heavy traffic congestion. So during this evening peak, they experience very long travel time in a busy day, like during the holiday. Okay, so this is a travel time of these two routes in normal day and busy day. And what is their route choice? As you see, the travel time is longer in the north route. So of course, most people take the south route. Most people prefer to take the south route. About 94% driver traveling from Hiroshima to Kobe takes the north route in a normal day. On the other hand, in a busy day, because of this heavy congestion during the evening peak, in the morning, in the most of the time, most people take about over 90% people take the south route. But during the peak hour, some people prefer to use the north route. So this is the route choice characteristics of these two routes in a normal and busy day. Okay. What is the accident risk in this route? And we calculated the accident occurrence risk and accident encounter risk for both routes. And the accident occurrence risk is for you to cause the accident is higher in north route. And as I mentioned, the north route, the road geometry of the north route is quite bad. Many curves, many steep curves, and uphill and downhill. And due to this road geometry condition, the accident occurrence risk is always higher in the north route. But if we see the accident occurrence risk, the trend is different. The accident occurrence risk, accident encounter risk is for you to encounter someone's accident. And this accident encounter risk is higher when the traffic volume is high. So in this case, the accident encounter risk is higher in the south route. So occurrence risk and encounter risk doesn't match each other. So this can cause the paradoxical situation as I explained before. And on the other hand, in the busy day, due to the heavy congestion in the evening, for most of the time, north route has during the off-peak hour, the accident risk of the north route is higher. But due to the heavy congestion in the evening, for most of the time, the accident occurrence risk in the south route is higher. Okay. And accident encounter risk is, of course, because south route has higher traffic volume, so the accident encounter risk is always higher in the south route. So in the busy day, for most of the time, the trend, the relationship of the accident occurrence risk and accident encounter risk, the relationship is same, matches for most of the time. I mean, the north route is higher compared to the south route for both risks. So in this busy day, we may not see the paradoxical situation, even if we provide these informations. So this is our expectation. And we tested this idea using a kind of simulation, not really the simulation, but we developed the route choice model considering the accident risk information. So the normal route choice, we mainly consider the time and highway cost. And in accident risk information route choice case, we consider the risk information effect in addition to the time and cost. And we conducted the stated preference survey to people using this route, and we estimated the coefficient of time, cost, and risk information. And this is a result of the estimation. And I will not go much in detail of this route choice model, but this is the estimation result. So, travel time, the coefficient of the travel time is negative. So they don't prefer the longer travel time, okay? And toll fee is also negative, so they don't prefer the higher toll fee. So that is very natural. And if you look at the accident risk terms, accident risk term is not so simple. So it can be negative, it can be positive. So yeah, but anyway, so this is the estimation result based on the stated preference survey. And we evaluated the effect of accident risk information by using this route choice model. And this is the result of the ratio of the when we provide accident risk information. And for the information type, we did 6 different cases. And we have 3 types of accident risk information: occurrence risk, encounter risk, and loss risk. So we have 3 types of different information. And also, we tested 2 ways of presentation. So one is just we provide the numerical number of each risk, and the other is a highlighted one. So we have three information types and 2 ways of presentation. So in total, we have 6 cases. Yeah, and we tested the route choice, impact of the route choice result. And this is the result. And so this blue line is the route choice result of when we provide encounter risk. And this is a south route, a probability of the south route. Okay, this is a route choice of normal case. So in most of the 94% of driver take the south route. So this is a current condition. And if we provide the accident risk information, in most of the cases, actually they don't change their behavior. Regardless of the accident risk information, most of the driver still keep using the south route. But if we provide accident encounter risk, they change their behavior, and the ratio of choosing the south route becomes lower. Okay, so this is normal day. Okay, and in a busy day, because of the heavy congestion in the evening, the accident encounter risk has very much larger impact. And during the congestion time during the evening, because south route experience very long travel time, very large encounter risk. So most people avoid south route if we provide the encounter risk. So most people take the north route. So this is the estimated result of the information provision. So only encounter risk has the impact, and accident occurrence risk doesn't have much impact because they are somewhere in this group. And only this accident encounter risk has some impact. And the second best information was the accident loss monetary information. And all the other information actually don't have much impact on the driver's route choice. So this is our estimation result of the accident risk information impact. And so that is the route choice, impact on the route choice. And our question is how much number of accidents we can reduce by providing the accident risk information. And this is a result. And without accident risk information, we expected number of accidents is this much, 0.379 in a normal day. And in busy day, expected number of accidents is 0.675. So these are the expected number of accidents without accident risk information. And below is with accident information. And we have 6 different information cases. So there are 6 results. And in most of the cases, the number of accidents slightly decrease. Like if we provide accident occurrence risk, the number of accidents, it doesn't change in this case, but in highlighted information case, the number of accidents decreases 0.1%, quite small change. Yeah, basically accident risk information impact is actually this much. But if we provide accident encounter risk, only encounter risk has the impact on the route choice behavior. And if we provide the encounter risk in a busy day, the number of accidents reduced 24%. It's a quite big reduction. So if we provide accident encounter risk information, we can expect quite big impact to enhance the road safety in a busy day. But on the other hand, in normal day, if we provide accident encounter risk, the number of accidents actually increased by 2.8%. The increase is very small, but still the accident risk information had a negative impact. So this is because of the information paradox, as I explained in the previous slides. So accident occurrence encounter risk can have quite a big impact in road safety enhancement, but it can have the negative impact if we don't. So we have to be very careful to provide the accident risk information. So that's one outcomes we found out from these case studies. Okay, accident encounter risk is very easy to understand, and it can change driver's behavior. But we have to be very, very careful. It can increase the number of accidents if we don't properly use this information. Okay, so this is some our study about the traffic risk information provision. And now I move on to how we can estimate the accident risk. And there are many research focusing on the accident risk estimation. And we can date back the research until 1970s or 1990s. So there are, for many decades, people were trying to understand how accident risk increase or decrease. And they found out that accident risk increase in a congestion flow. During the congestion, accident risk can increase, or during the rainfall, during the rain weather, accident risk increase, or the speed has some impact, or the boundary between free flow and the congestion flow has a higher accident risk. So we have many knowledge about the accident risk. And to estimate the actual number of accident risk, there are many models based on the Poisson regression model or some other statistical method. So there are many research accumulation in this field. And for accident risk estimation, the most popular way is the utilization of generalized linear model, like multiple regression based model or logistic regression type or Poisson regression type model. There are many models proposed depending on the dependent variable, depending on what they want to estimate. If you want to estimate the accident risk, then the multiple regression can be used. If you want to estimate the number of accidents, Poisson regression can be the choice. So there are many research, there are many models proposed. And the independent variable or the explanatory variables are like the road geometry or the traffic condition or the weather condition. By using these variables, people are trying to estimate the traffic accident risk in the literatures. But there is a limitation actually in these models based on the generalized linear model. Because in these models, basically, they consider many independent variables to develop this model, but actually most of the variables are just considered as a linear combination of these different variables. Okay, so yeah, traffic accident risk is explained by the linear combination of these different variables. But traffic accident is not that simple phenomena. The accident risk can increase by different combination of these factors. So we have to consider not only the linear combination, but also we have to consider the interactions between different variables, like interaction between curve and the rainfall and the heavy traffic. We have to consider this interaction. But in a generalized linear model, we can only consider the limited number of interaction terms. It is very difficult to consider all the possible combination it is technically really difficult. So this is a key limitation of the types model. On the other hand, in these days, about 10 years ago, the deep learning model becomes very popular. And in these deep learning models, basically this model is black box. We don't know what is happening in the model, but this model can consider all possible combination of the independent variables. So we can consider the interactions to explain the accident risk by using the deep learning model. So this approach is becoming very popular in traffic accident risk estimation research field. So we also did some works. And this is a concept of the accident risk prediction model. In our model, we input the traffic condition data, traffic data of past 1 hour, and we input this past 1 hour data into the AI model, and the model outputs the future accident risk, like half an hour in the future. Accident risk in half an hour in the future. So this is our idea of the AI-based model. So by inputting the past 1 hour data, we predict the future accident risk in half an hour. And this is our model. So we utilize the convolutional neural network, and the input data is volume, speed, occupancy, or time of day, or weather, or some other factors. We input these factors. And through the CNN model, and at the end of the model, we output the probability of the accident occurrence in half an hour in the future. So this is the overview of our accident risk prediction model. And we developed and tested this model using the Expressway data. And this is our data, and there are 4 sections, and each section is about 15 to 20 kilometer length. And we developed the accident risk prediction model for each section. Okay. And we utilized the 9 years data of accident records and 5 minutes traffic detector data, which consists of count and occupancy and speed, and also the weather data and some other data. Okay. And this is a prediction accuracy, and there are many different ways to present the accuracy, but this is one way of to show our performance. And this graph is a bit complicated, but x-axis is the accident probability that the model output. So, okay, x-axis is accident probability, predicted probability. Okay, predicted probability. And please ignore the bar chart. Please ignore the bar chart, but please look at this line, which is right-hand side. The axis is right-hand side. The axis on the right-hand side represents the actual probability of the accident. So x-axis is the predicted probability, and y-axis is the actual accident occurrence rate. Okay, and if the model output like 20% of accident, so this is this part, which is this part, the model outputs the 20% of accident, then in this case, the accident actually occurred in 20%, in 20% cases. Okay, if the model outputs the 15% of accident risk, then in reality, the accident occurred in 15% cases. So this is our model performance. So the model output, the probability that the model produce is quite consistent with the actual accident rate. So yeah, this is our prediction accuracy, the prediction accuracy of our model. So the model output can be considered as the accident probability, like the probability of the rainfall. Okay, now we have the accident prediction model with a good accuracy, but the key limitation of our model is we don't know where the accident occurs. Okay, the accident prediction is conducted for this big section, And each section has about 15 or 20 kilometers. And we can successfully predict the accident probability within this 15-kilometer section. But we know in this 15-kilometer section, the accident may occur in somewhere in 15 kilometers, but we don't know the exact location from this model. But we, of course, we should have the accident location to identify, to conduct the effective countermeasure. We have to know the accident location. So that is the key limitation of our model. So how to identify the location with higher accident risk? This is the next question. And again, this is our test site. So we focus on this 15-kilometer section to develop the accident location, to identify the location with higher accident risk. And for this study, we only used 2 years data from 2020 to 2021. And during this period, we observed this number of accidents, about 400. And for this study, in the previous study, we utilized the detector data. But for this study, we utilized probe trajectory data, around 25% penetration rate. We have nationwide probe vehicle data in Japan, and we utilize that data. And in the highway, we have around this much penetration rate. In urban arterial, we only have a few percent penetration rate, unfortunately. But on the expressway, we have quite good number of penetration rate. And this is a actual probe trajectory of our nationwide probe data. And yeah, x-axis is time and y-axis is location. So as I explained, this location consists of 15-kilometer length. So this trajectory represents whole traffic state of that study section. And x-axis is a time. And here I show the 1 hour data. Okay. And actually, instead of using the detector data, in this study, we utilized this detailed probe trajectory data to identify the location with higher accident risk. And the idea is the same. We input this trajectory image into the accident risk prediction model based on the CNN model. Then the model outputs the future accident risk in half an hour in the future. So basic idea is the same as the previous study. Okay. So the model output is still percentage of the accident in 15 kilometers. So this is a key idea. And let me skip this part. This is a bit complicated. And the prediction accuracy is this much. X-axis is a predicted probability, and y-axis is the actual ratio of the accident occurrence. And this model also produces a good accuracy of the accident probability. So if the model outputs the higher accident risk, then the actual ratio of the accident occurrence also increases. So the model output actually consistent with the actual accident rate. So we confirm that the model, this new model also produces a reasonable level of the accuracy. But still, we don't know. We can estimate, we can predict the accident probability, but we still don't know which location has a higher accident risk. And how we can estimate the location with higher accident risk. So this is the next question. And okay, we developed this model by inputting the probe trajectory image, and the model outputs the accident probability half an hour in the future. But we want to know in which location the accident risk is particularly higher. And to know that, we used the Grad-CAM. The Grad-CAM is one type of the explainable AI, and I will show you the simple example. So in this picture, we have dog and cat, and the model outputs if this image contain cat or not. Okay, and of course this image has a cat, and the AI also output in 98% this image contains a cat. Okay, and by applying the Grad-CAM, not only the probability of containing the cat, but also we can know in which part of the image the CNN is focusing on to produce this output. And in this case, okay, this CNN is focusing on this part to make this 98% probability. Okay, this is cat is there, and to make that probability, the CNN is focusing on this part. So now we know, okay, the CNN is focusing on this part and produce that output. Okay, and we utilize this Grad-CAM technique to our accident risk model. Similarly, our model, the input to our model is this image, is this diagram. And our model produce future accident risk is 60%. And by applying the Grad-CAM, we can visualize the contribution map of the CNN. Okay, and if we so now we know to make that 60% output, the CNN is focusing on this area, this red area. So this is the information we can get from Grad-CAM. And by utilizing this Grad-CAM contribution information, we can estimate which part has the highest accident risk. And in this example, okay, this part has the highest accident risk. And by comparing this predicted location and actual accident occurrence location, we can calculate the distance error to validate our method. So this is an overview of our accident location identification method. Okay, this is best example actually. The diagram in the left-hand side is the input trajectory image. Okay, this is the input data, and the figure in the middle is the contribution map that Grad-CAM produced. So from the Grad-CAM, this part, and this part are dangerous. I mean, they are focusing on here, here, and here. And if we go back to the input data, this is correspond to this part, and this part, and this part. And if we closely look at these parts, actually there is some small congestion is happening. So this contribution map looks quite reasonable to estimate the location with higher accident. And actually, based on this contribution map, we estimated the future accident location, which is this red part. And this is perfectly corresponds to the matches the actual accident occurrence. So this is one of the most successful case. And yeah, this way we evaluated our method. Okay, and yeah, so this is just evaluation using the best case, and we evaluated the case using the 400 accident cases. And this part is a bit complicated, so let me skip. And so this is the proposed model, and we tested this method against the statistical data. From the statistical data, we can also know the dangerous part based on the accident record. And we tested our proposed method against the accident location, expected accident location based on the statistical data. Okay, and this is a result, and the distance error of the accident location is this much in our proposed model, and this is the accident location estimated from the statistical data. So at least our method performs better compared to the statistical data method. And to be honest, the statistical data can perform quite good to estimate the accident risk. But our method is at least outperforming the statistical data. And also the good point of our method is we can visualize not only the most dangerous part, but also we can visualize the second worst part or dangerous time and space. So this information can be utilized further. So that is our ongoing research. So yeah, this is the end of my accident risk information, accident location identification study. Okay, I will skip this. So in the first part, I explained what is the accident risk information. And in the second part, I explained our recent research activity about the accident risk prediction using explainable AIs.